Hey everybody, Dr. Retzig back with you. This is our 8th video in Math 406 and the final video in section 6b. So this is a continuation of section 6b. And this last video, this is about what's called the Riesz Representation theorem, which is an absolute classic in the study of inner product spaces, or more generally, in the study of what are called Hilbert spaces. And the theorem actually illustrates a very general principle, which is easy to spot in simple examples, but just holds with absolute jaw-dropping generality. So let's get our bearings straight here. We need some words first. So here's a vocab word. A linear functional. Linear functional. So that's the term we're defining, a linear functional on a vector space V is simply a map. Phi is the traditional letter belonging to the space of linear mappings from V into the scalars. So when you have a linear mapping that spits out actual scalars rather than vectors, you call it a linear functional. So here's a nice example. Consider Phi mapping, how about R3 into R by, okay, so here's the drawing. So here's R3, and Phi acts on R3 and spits out answers that are just simply real numbers. So here's R. People usually draw R with a number line, but it's just a big box of stuff like any other vector space. Here's how Phi works. If you plug in a vector from R3, say the vector xyz, here's what Phi does to it. You feed Phi xyz, and Phi will spit back out x plus 2y minus 5z. So you see the right-hand side of the equal sign, that's just some number. So that's the output. So this vector by Phi gets sent to this answer over here. So you can see 0, 0, 0 goes to 0. 1, 1, 1 goes to what? -2. Basically, just plug in any ordered triple you want, and Phi will send it to some number. Now, it's easy to check that this Phi is linear. Remember, linear means Phi of thing 1 plus thing 2 is the same as Phi of thing 1 plus Phi of thing 2. And Phi of scalar times vector is the same thing as scalar times Phi of vector. You can check those things. This is linear. Okay, it's worth observing, though, that Phi in this example is simply a dot product. It's simply an inner product with a very certain vector. So notice this. Notice phi of xyz is nothing other than xyz inner product 1, 2, -5. So even though phi had this formula that looked like kind of an algebraic formula, phi was really just inner product with the vector 1, 2, -5 in disguise. So that example's nice. That one, the linear functional, just turned out to be an inner product with something very specific. So to get from the left-hand side to the right-hand side in that drawing, you just dot product with this guy. That's how you move to the right. Pick anything you want on the left, dot it with that one thing, and that's where you go on the right. Delightful. Even more delightful and amazingly true, this always happens. Where by this, I mean anytime you have a linear functional. Anytime you map an inner product space into the underlying scalar field, your mapping, no matter how crazy it looks, is simply inner product with some specific vector. And that's known as the Riesz Representation theorem. And that's our big prize for the day. So here's the Riesz Representation theorem. Riesz Representation theorem. Now, this is our version which applies to finite dimensional inner product spaces. The theorem is actually true in some greater generality, and we're going to need some additional machinery to state that greater generality, but at the moment, we certainly have this. Let V be a finite dimensional inner product space. So this is just a vector space that happens to have a working inner product on it. And phi belonging to linear maps from V into the underlying scalar field, a linear functional. That's it. We know nothing specific about these. Okay, under those hypotheses alone, then there exists a unique vector U belonging to our inner product space such that if you want to see what phi does to a vector V, you only have to inner product against U. And this is true for all V in V. Back in this example, this orange vector here, this is playing the role of the vector U. To figure out what phi does to an arbitrary xyz, all you have to do is inner product with that guy. And the Riesz representation theorem is saying, yeah, this always happens. Okay, let's prove this. The proof is so clean and lovely You can't even believe that you're purchasing this really broad abstract statement at such a bargain price. Here's the proof. Let's do it in black. Proof. All right, since V is a finite dimensional inner product space, we know V has an orthonormal basis. So let's just call one out. Let E1, E2 through En be an orthonormal basis for V. This is a perfect illustration of why one might like to work with orthonormal bases. Okay, so we've called out an orthonormal basis. Now, let phi be a linear functional. Anything you want, no specific formulas. All you know is that you got a linear map from V into your scalar field. That's all you know about phi. Finally, we're trying to show first this for all statement. So this is something that's supposed to hold true for every vector V in big V. So let's just grant ourselves an arbitrary vector, little v, in big V. Suppose little v belongs to big V. Well, since E1 through En is a basis, certainly you can write little v as a combination of E1 through En. And since you understand orthonormal lists and you are now masters of section 6b, you even know what linear combination it is. You know that V is nothing other than V inner product E1 times E1 plus ... V inner product En times En. That is the linear combination of E1 through En that comes out to V. That's how you find it. That's the beauty of an orthonormal basis. You know the coefficients. You just get them by inner producting with the basis itself. That's fantastic. Okay. Well, if that's little v, let's do phi to it. Now remember, phi is linear. So phi of that giant linear combination can be broken up into little tiny phis of each individual piece. So imagine phi hits this first. Well, V inner product E1, that's just some number. So phi of that first piece is simply V inner product E1 times wherever phi sends E1 plus ... And remember, when we get to this last piece, this part is just a number. So when you do phi to the last piece, that number comes out in front. Phi is linear after all. And then you just have phi of En. Oh man, but this is so nice. Look what these are. Phi is a linear functional. Phi outputs scalars. So phi of E1, that's a number. And you can cram that number back into the second slot of that inner product. Now remember, you got conjugate homogeneity in the second slot, so that comes in like this. Inner product V, phi of E1 bar times E1 plus ... V phi of En bar times En. Oh, but you have additivity in the second slot. That's what an inner product is after all, so this is nothing other than V inner product with the single vector phi of E1 bar times E1 plus dot 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 phi of En bar times En, and this, that is nothing other than U. That is the vector you should inner product V with to represent phi of V. So not only have we shown there is a U, we even know what it is. It's that combination of E1 through En. Just do phi to each of them, conjugate, and use those as coefficients in a linear combination of E1 through En. Now, there is one additional piece. Supposedly, that's the only vector that can do this trick. So we have to argue uniqueness, but that's super straightforward. Doesn't have anything to do with orthonormality or anything like that. If phi of V were to somehow be equal to inner product of V with some other vector U hat also, then we would know V with U, the one we just found in purple, would have to agree with V with U hat for all V, which would imply inner product of V against U minus U hat would be 0 for all little v's. And in particular, if little v were equal to U minus U hat, we would have U minus U hat inner product with U minus U hat equal to 0, which would imply the norm of U minus U hat is 0, which would imply U is equal to U hat. So that secondary vector that we hypothesized might also do the same trick. That U hat's an imposter. U hat is U. So not only is this purple vector here good to do the trick, there is no other vector that can do the trick. And that's the Riesz representation theorem. I invite you to read some of the striking examples here in the last section of 6b, where you just can't even believe that there's a vector that could play this role. And yet this proof tells you exactly what it is. You should check out those examples. They're pretty rock solid. All right, that's it for Riesz representation theorem, and that is it for section 6b. All right, moving on to section 6c. I'll see you next time. Bye.